Okay, let me restart um, just reconsidering a few words about the lecture of last time. Now, let me share. Yeah, do you remember last time after uh, in a long introduction, which we have seen what is the model, if this model is correct means true, if correct means valid. I don't have now time to repeat everything in detail, but if you remember, I try to introduce the concept of a model for a system, a model for for a system. Do you remember the difference, validation, verification? And in particular, yet now one word more I would like to spend here. I told you that in this part of the course, mm, we will see the descriptive statistics as a method to build a non-parametric model. And a model is a description of the reality. Boom. Keep in mind, remember last time I insisted a lot of this verb theme, this wording. Is a description of the process, of something which I would like to control. I would like to monitor. It doesn't matter which one. Could be an economical system, could be a biological system. Very important that they will see what I intend is something which I would like to describe, very, very general. Now, here in this slide, do you remember I told you now we will concentrate our identification methods, or the method, because we will see one method, even though with some different aspects, considering in a particular family of models, non-parametric models. Yeah, the non-parametric models is a definition, a nomenclature. This is a little bit confusing because we will see, we see last time that nevertheless I have to do with parameters. Why the name non-parametric model? We can understand very well when we will consider the parametric models because the difference is that in case of non-parametric model, we have parameters that they are not directly connected with let me say, the physical meaning or the meaning of the system which we are considering. Let me show you this concept again here. The idea is to introduce this non-parametric model. Last time I considered these measurements, 1, 2, 3, 4, 5, 6, 7, 8 measurements, these Y measurements, and I try to formulate the problem just roughly. Please calculate or describe this phenomenon, which is characterized by these 8 measurements. Measure 1, Y1, measure 2, Y2, measure 3, Y3, Y without measurements. Using a model, as a model in our case, we will see, I told you last time, is in a function. Model equals function in our case, because we're here speaking about mathematical model. Now, remember last time I told you, for us, model means mathematical model. Model is not only, when you speak about models, we have to think that not only the mathematical models are model. Model is also in a graph. It's a representation. Model is a representation. But in our context, our mathematical models, here we have just one model, isn't, excuse me, our models isn't a mathematical model, or they are mathematical models. Here is an example of one of them. This means in our case, the idea is, or the exercise is to calculate a mathematical model, in this sense, to calculate A0, A1, AN parameters. I don't know if you remember Taylor, polynomial. Polynomial is clear what I intend for polynomial, no? For everybody from gymnasium, polynomial. But that is just in a family of possible mathematical models. You remember exponential models, I can consider a sum of exponential function. Or we will see in this course sine, cosine functions. Also, this is a possible mathematical model. Now, the question is, today, again, to calculate A0, A1, AN, such that I will obtain the best model. Clear. So formulated is quite stupid, because what is the best model? Do you remember last time I told you this sentence doesn't mean no meaning, because the best model means to define, and the cost function means to define criteria in order to say this is better than the other one, this is better than the other one, is worse than the other one. So formulated, no meaning. We will see now to give a meaning on this sentence. N is given, but also n, the exponent, the order of the polynomial, should be something to be optimized. Why the best, if I am able to define somehow the best, should be the order number 2 or number 3. Also, n should be calculated in an optimal way. Do you remember that the question was in this slide here? I try to repeat back quickly. What is the best model, the best mathematical model? The left or the right one? The best answer is always it depends. Even though you notice on the, I don't remember who, with 2 points, of course, we will see that the statistics, the word statistics may make sense. This means with 2 points. It depends, of course, which kind of phenomenon I have to describe. But in general, 2 measurements, in particular in technical context, is clear. It's extremely limited information about the phenomenon. Do you remember statistics? Of course, if I consider the word statistics, you know from Gymnasium, from other courses, theoretically, this measurement theoretically should be tends to infinite, to speak about the truth, but infinite doesn't make sense for us. Anyway, should be a consistent number of measurement. What is the meaning of consistent? We will see. Because consistency is also in a category, and in the word has no meaning for us. 3, 4, 5, 3, we will see together. But anyway, in any case, I can say that in general, in particular for physical system, technical system, in which the phenomena are continuous phenomena, 2 points, 2 measurements is just. And a rhetoric question and the didactical question. I mean, look at this example here. Do you remember I told you here we have X exploration variable, the current. No? Excuse me if the examples are more oriented for engineers, but I am an engineer. X represent the current, and Y the measurement, Y1, Y2, Y3 are the flux of the motor. Of course, we can understand that these variables, they are continuous variable. I can consider current changing from 0 to 8 ampere, continuous, no? with the milliampere, nanoampere. No? This means we have a function which appears continuous. This means if I consider just 2 measurements, of course, we have just really the partial information about the phenomenon. Also with 8, but better than 2, it's easy to understand. Let me go ahead with the calculations now, because I would like to tell you many things today. Nevertheless, the question, which I will reconsider in a few minutes, yeah, makes sense. What is the best one? The answer is depends, because we have a drawback. Do you remember last time I tried to introduce the answer? And advantages in both cases. No? Look, here I tried to slow down a little bit because we did this, but I received some negative feedback in the sense that not all students are habituated with this language. This is a mathematical language. Why that? Because, as I told you, our models are mathematical models. Now we fixed 2 things that we will see must be optimized. We fixed the family polynomial. I can say why polynomial. I have to to be able to answer why polynomial in this case. At this moment, I didn't give any reasons because as an example. And when I have the polynomial, do you remember I told you which order? I fix n is given. N is given, could be 2, could be 3, could be 5. Don't care about the optimization of n. Don't care about y polynomial. And then we will see later this aspect here. Because before speaking about these difficult aspects, I have to clarify, again, last time I introduced, nevertheless, what is the problem? What is an optimization problem? And what is a convex and not convex optimization problem? And then slowly we go ahead. Again, polynomial given. I am a dictator. Must be done with a polynomial. Order n. What is n? It's given, but it's n. You think 3 is okay, 4 is okay. We will see with MATLAB a little bit later. Now, what we have here in this representation, if you have a question directly, no problem. In this representation, we assume that not necessarily the best model y hat. Y hat is the function. No? Hat in our literature indicates always the approximation, because the function, the blue function, is an approximating function, is the regressor. Another word which we will use, regressor. Regressor equals approximating function. Function equals model. And in the context of mathematical models, of course. The model is also a scheme. I can draw, I can graph. Here we are in the context of mathematical models in the sense. Here, I assuming that not necessarily, it's just why I'm assuming this, excuse me, not necessarily the blue line should meet all points, all measurement, or some of them. This assumption is not conservative. Conservative means in our context, that is the flexible assumption. This means if I consider a blue line in a function which meet some points or all points, it's a particular function. It's not a general function. I mean, after my calculations, we will see now what is the meaning of calculations in the constant optimization. If the results of the calculation, the result says to us that the blue line should meet some points, all points, we are satisfied. But at the beginning, I will consider a more general problem in which I will try to minimize in a function, we will see which kind of function, which will consider the error in the sense the difference between the points, which are measurements, and the corresponding point on the blue line. If after the calculation, I will discover that, for instance, this point here is exactly on the violet point, of course, we are satisfied. But at the beginning, I cannot say where is the blue function. This means this difference here between y1, this is y1. No? I didn't put it, but this y1, y2, y3, y in general. This y1 we will write mathematically as it circa, not exactly. No, not exactly. This symbol means not exactly this point here in general, no? At the beginning, because I don't know where it is. This point here, which is y hat, this is the model, calculated at xi1. This means a0 multiply x1 up to n, plus a1 multiply x1 up to n minus 1, and so on. I do the same here. This means y2 is circa, not exactly, this point here. What is this point here? This point here is x hat calculated at x2. This means a0, the same a0 as before, because I will look for one function. It's too difficult what I have explained a little bit. No? We can understand me a little bit. Ask me, no? Because the idea is everybody should understand. Everybody. Deterministic approach, everybody. I try to trivialize, to repeat, because I know that not all students have the same background. For engineering, probably it's boring, I think. But not all students are engineering. This means A0 as before, multiply x2 up to n plus A1 multiply x2 up to n minus 1, and so on. I do this the representation is not yet calculation, but it's a calculation somehow, symbolic calculation for all measurements, for m measurements here. The m equals 8 measurements, but assuming that I have m measurements, could be 10, could be 100. Look, what I try to explain with words is written here. Here I repeat it for you, the model, the general model, and then I exactly write, I write here m conditions. We say in our context constraints. Now we will clarify the words also, but condition it probably is more for you is known what is the meaning of condition. Basically means this is the general expression of what? Of, again, this point here, which I don't know where is. Could be here, could be here, could be here, could be also on the violet points. I cannot assume directly at the beginning. Could be. I do the same for, as I told you, for all my measurements, which I assume to be m. y1, y2, ym in our representation, m equals 8. Could be 9, could be... Of course, if I have more information, theoretically infinite information, I don't want to say that I have the truth, we will see, because the measurements don't represent the truth, represent the measurements. But anyway, I have more information. More information is better than less, because if I don't need, I can throw away. Statistically, we know what I intend, you know. Okay, now this language is okay, no? This language is, we can understand. This graphical representation, which is still in the model, is already in the model, was already in the model. Now, we can understand better what I intend. Look, from this slide to this slide, last time I tried to explain, I explain again. The information is the same, but I translate it. Basically, at this moment, I did two translations. From this model here, from this language here, to this one. This is clear. Now, from this language, I translate it in another language. If I translate, you can use different notation and wording. I should have an advantage. Why have I to translate if I don't have an advantage? In math, it's always so. I do something because I have some, at least no drawbacks. What is the advantage here? The advantage here, and now I will tell you that is exactly the same information. The advantage is in this form. We can use the computer. Today we will do. I will show you the map. Why that? Because the computers, any software, in the microcontroller in general, we can represent in a suitable way the information organized in tables. Which kind of tables? Matrices and vectors. About matrices and vectors, you know everything. But you heard about tables. And the matrix in the table. And the vector is also in a matrix. This is a particular table. Could be the column, could be the row. Think about it. Tables. Yeah, the advantage is clear because I can, well, it should be clear in half hour when I will open MATLAB. Really, MATLAB understand exactly MATLAB or any kind of computer language, tables, matrices, vectors. In particular, MATLAB. MATLAB means matrix laboratory. Here, the language of the matrices is understandable from MATLAB. Otherwise, why the name? Yeah. Why now the information which we have here is the same, but is in a more suitable form. Now, because if you remember here on the left, it's quite clear what I intend, because here we have a vector. It's the vector of the measurements. I organize my value is a column vector, y1, y2, ym. I called this vector y capitalized, underlined, but in the book you can find a different notation. Circa, you can understand, I compacted this m times circa, or more or less, in one. I don't know if you remember the language of the matrix. This is exactly the language of the matrix, in which we have here it's clear this is a vector equal more specifically y1, y2, ym, and this in this form you didn't see. You have seen just equals, but here it's not equals, it's circa, because the problem is a bit different. Now, if you remember the rule row multiply column, row multiply column, I repeated it also last time, it's clear that if I do this row multiply this column, I don't want to now to repeat, think that I already repeated last time. I will obtain this information. If you remember the rule, row multiply column, first component of the matrix multiply first component of the vector plus second component multiply the second, and so on. Should I repeat? I think you know, no? If it's not clear, I repeat. Row multiply column. Should I do with the lateral camera? No. It's okay. And if you apply the rule at, let me say, at the matrix, this means to all row, you obtain exactly the first information, let me say, the first line, you will obtain the second line. And what is the advantage here? The advantage here that I have now a more structured information, in which sense? That we have a column of the measurements. Here we have a matrix. This matrix, in some literature, in some books, the name is exploration matrix, because it's a function we can see of the x element, x1, x2, xm. Remember, I called this exploration variable, the current. I did last time also another example. You remember, consider x as the time, and why the level of attention of the student in the lecture, no? Because through the time we have a saturation. It is already good result, because very important that does not decrease the attention. No? Just to understand, could be everything. Measurements based on exploration variable, not necessarily current. Also the time could be also everything. Another example, I don't remember. Now I don't have in mind, but we will see during the semester. Everything. Another example, last time I did, but it doesn't matter, no? But the example of the attention over time makes sense. No? I speak saturated. Saturation is not bad, because never let the bad is if the attention will decrease, no? Over time. Now, very important here to notice that I have an exploration matrix, and I have a matrix of the unknown parameters. Theta, I formalize here theta vector, x capitalized vector, theta capitalized, and y capitalized. Everything is underlined, because in some literature, sometimes I forget, the vector or matrix is underlined, but it's other books, different books use different notation. About the notation, don't care much. We will see, very important for us is to understand how we can use this knowledge. In fact, we will do projects. I told you that last semester in this course, no, for the course, no, in this course, we received the best paper award with a student of this course. Now I will go ahead, but I will show you the paper which we generated, and also is also in my own page. But now the direction of the complementary study propose an interview, and in the next weeks will appear also interviews of the students. I will show you to motivate you to remain, don't drop out the course, because we can do a very interesting thing. Of course, that's nothing to do with the examination. We worked also later because of course for the examination you don't need to produce any papers, just to show me that you are able to produce results on a problem which is connected with the course. Okay, look here, very important here. In this particular representation, if n is given, please pay attention, if n is given, we have a separation between what I know and what I don't know. This is always a very important concept in science. I don't know if you remember in high school, you have an equation, an x. To calculate x, we have to isolate the x on the left and what I know on the right, such that I will calculate what I don't know x as a function of what I know. But if we're not able to separate, we can be able to find at least a solution in analytical form. We have to proceed numerically. At Gymnasium, we didn't do that. I don't know here in math, probably. Yes, I don't know if it's clear. I have an equation. Should I write x squared plus x squared plus 2x plus 1 equals 0? We know that there is an PQ form. No? PQ form is clear what I intend, or the ABC form. To calculate what x as a function of what I know. What is what I know? The coefficients of the polynomial. Should I do? If I write x squared plus 2x plus 1 equals 0, 1 multiply x squared, 1 I know. 2 multiply x, 2 I know, the factor 2. Plus 1, I know 1. You remember, yeah, we can consider P and Q, no? And then I can calculate x as a function of what I know. This is very important principle in the science, to be able to separate what I know with respect to what I don't know. Here is, if n is given, 3, 5. In this matrix, I have everything which I know. In this vector, I have, in the other side, in the sense of the output. Output is the measurements, what I know. And here, I have what I don't know. This means this part here is what I know in output of the phenomenon, level of attention, flux, density, everything which I consider in the system. Here is what I know in the input, exploration. Input equals exploration. I put current, I received in output flux. When we are able to divide what I know and what I don't know, we are in a quite good situation, because somehow it's clear or it's separable again, and a possible solution, which in the optimization problem is not necessarily easy to be calculated, but in any case, an advantage. If n is not known, should be calculated, we cannot say that we can separate what I know with what I don't know, because in this matrix here, we mixed what I know, x1, x2, xm, and what I don't know, n. If n must be calculated, assume that is given. Now, the topic, the question is to calculate a0, a1, an. It's the unique element vector or elements of the vector which must be calculated if n is given. 3, 4, 5, doesn't matter what. Now, you can see here in this part of the slide, as last time I told you, if I consider a cost function which must be minimized, in which y represent exactly my no measurements, x theta represent my possible point with lie on the blue line. I don't have time to show you with MATLAB, but intuitively, I told you also last time, if the function to be minimized is the linear error, we don't have solution. Yeah. This underline, this here, this is easy because here we have 1, x1 was 1, look. It's quite clear, no? x1 there is 1. This means here we have, good question, excuse me, 1 up to n could be everything, but it's fixed, 3, fixed 3. Here we have 1 up to 2. 1 is clear with this. What we have here, x2. Let me see x2. It was 2 probably, no? 2. This means now it's clear that this element here is 2 up to n. And was 3, no? I fixed. I don't remember. This means 2 up to 3 is 8. We will see that MATLAB does in 1 nanosecond. This is 2 up to 2, 4. And so on. Then we have 2 up to 1 and 1. Did you answer?
Oh, like how do it combine these when they
Yeah, I told you.
like
This is not to calculate, it's just to calculate. Yeah, it's exactly what I told you. You have to consider the value x1, x2, xm. Did you see this vector? x1, x2, xm. This vector, each element up to 3.
also every of these elements is like underlying these, and it can every time.
No, this is calculated once, always. Once, just once.
These are the measurements.
The measurements. The value of x. The matrix X, good question, is the matrix of the exploration variables. Up to, you have to read here. Again, concretely, this is 1 up to 3, 1. 1 up to 2, 1. 1 up to 1, 1, and 1. Second line, 2 up to 3 is 8. 2 up to 2 up to 4 up to 2 is 4. 2 up to 1 is 1, and 1 is 1. And you go ahead. This means, we will see in MATLAB now, it's easy to be calculated. You have to just to calculate is a good word, but you have to type. Good. Now, do you remember last time I told you if the function to be optimized, to be minimized, is a linear function, you will not find in general a solution because the minimum here is a linear function in theta. This means if you do the derivative, you remember in gymnasium to calculate the minimum, if the necessary condition is not sufficient, but necessary to do the derivative. Remember, if you want, I can, for student who is not happy with math, I can. But this is in a point. When I write this expression, this expression here, to calculate the minimum as a function of theta, is a linear function of theta. In order to trivialize the concept, think about this. Just to trivialize the concept. Which I know, just to do an example, otherwise I have to spend energy. 1 it doesn't matter, just one measurement. X multiply theta. X is given, X is no. This means, it's your question, X is no. If I were to calculate with respect to theta, what I have here? I have that the derivative of this expression, which I will call E, for instance, no, the error. And I put equal 0. Do you remember in gymnasium? A necessary condition is the derivative equals 0. And then you have to look at the second derivative, third derivative, in order to classify if it's the minimum, maximum, and so on. Do you remember this a little bit? You don't remember? The derivative, you remember the derivative? When the derivative is 0 of a function, we have a minimum, or we have a maximum, or we have a settled point, and it must be classified. But in any case, the necessary condition to find the minimum or maximum, we are looking for the minimum in any case, because we want to minimize the distance. Because the idea is to find the best approximation. We do the best approximation, assuming that we consider the best approximation the minimal error. But also, the minimal is not a clear concept as long as we don't define the cost function to be minimized. Here we can see that in this case, if the cost function is a linear function, the error is in a linear function of theta, we have x equals 0, but x is not equal 0. I told you exactly that it's in a matrix, full column rank. About that, forget. But we will see this notation, this wording later. We can see that's in a contradiction. If it's in a contradiction, no solution. X equals 0 is in a contradiction because I told you that x is not equal 0. If you look at the matrices, it's a little bit difficult at this point. Again, my goal, excuse me for the engineers, is that everybody should understand me. If you have complementary for engineers, it's trivial, I understand. But we are here for everybody. No? This is the goal. 1 second. But I think that nevertheless, also for engineers, another point of view, it could be also interesting. Look at this. Why is it a contradiction? It's a contradiction because if you look at directly at this matrix here, already this one say to us as not 0. Cannot be 0. Now, how we can, should I repeat a little bit this minimum maximum? Could be useful. For engineers, boring, but how we can calculate minimum maximum of this function here? As a function of x in this case, not theta, as a function of x, is not a problem. Here the variable is x. Here the variable, in accordance with our lecture, our notation, was theta. X was given. You remember your question? X was given, must be given. I have to put equal 0 the derivative. Do you remember in gymnasium? No, you don't remember. Here, the problem is consistent. Why is consistent? Because we have the convex function. The convex function. But in the line, it's not consistent. If you consider this function here, we have 1 equals 0. Exactly what I told you before. If I try to put equal 0 the derivative of this, in accordance which we learned in gymnasium we learned that maximum, minimum, settle point the same. To find this, necessary condition is to have the derivative equal 0. And then we have to classify using the second and so on. If I'm in the line means in the linear function of the parameter of the parameter or variable which I want to optimize. We can see that 1 equals 0, no solution. Remember at the beginning I told you if you consider the cost function to be optimized in our optimization problem, which is linear, no chance. Now it's more clear what I intend. Excuse me if I repeat, but I received some emails that some students don't understand anything what and that I have to clarify because I am not here for just for engineers. Excuse me if I repeat again. Question me. This is the sense to be here all together. Now it's more clear what I told you, no solutions. 1 = 0. We cannot give them a meaning. We can do some effort. In some context could have a meaning, but here no. Okay, let me go ahead because the idea is to really go ahead, but it makes sense to clarify some basic knowledge. Now we can understand that if I have a convex function to be optimized, I can have the possibility to find a solution. Here, do you remember last time I tried to distinguish between convex and not convex optimization problem, which is the problem is related to the function to be optimized, but is related also to the constraints. Now, here in our problem, in our course, it's a little bit more difficult than in Ginasio. In Ginasio, I repeated very quickly how we can find the minimum or maximum. If I consider instead of x squared plus 2x plus 1, if I consider minus x squared plus 2x, I will have a maximum. If the function is not so, but is so. Here is not only the cost function important, because the cost function I introduced just here, and the cost function we cannot help to find the solution. It's clear now, we cannot help. But here we have also the constraints or the conditions. Constraints is the word which we use typically. This means we have not only the cost function as in Ginasio, we have something more complex. Because I would like to find a possible solution of our minimum, but x theta is constrained here. Or let me say, the function which we want to find should satisfy these conditions here. Therefore, we say that we need necessarily a convex cost function, but also the constraint must be particular. I already answered you about the constraint, because the constraint should be constraints in which I can see this separation between what I know and what I don't know. And then I can speak about the convex optimization problem. What is the convex optimization problem? Is in a problem in large, which we have just one solution. But of course, could be convex also in some regions. Just we understood again what is in the convex optimization problem. I already told you now. Now, here we can see how I can define a cost function which is a convex function. Typically, we are considering an error square, or better to say the sum of the error square, considering now the vector E transpose multiply E, which is basically expressed better, if you like, here. Last time we concluded here, which we can see in more, I would like to say, common language. The sum of the error square is here, between what? Yk, which is here, yk1, yk2, yk3, and the corresponding y hat k. This square plus this square plus this square. Yeah. This is the typical way in this method, the least square method, and typical way in order to obtain at least a convex function to be optimized. This is a necessary condition. If the function is not convex, of course, we don't have one solution, or in the worst case, we don't have solutions, but we want to have a solution if we want. Now, this part here I would like to skip. Last time I told you the calculations I don't need to do. I just would like to repeat this concept here, that this condition here, which typically is just a necessary condition. I told you before, in Gymnasium, we learned that the derivative is necessary, is not enough, not sufficient, because we have to check second, third one, and so on, in order to classify if it's minimum, maximum, and so on. But if we know that the cost function is a convex function, we know that we have one minimum. Assuming that the constraint are organized or can be organized in which we can recognize what I know and what I don't know. At the end of these calculations, which I don't want to tell you, but engineers probably can ask me or should a little bit analyze also this calculation, I can find in this particular structure, cost function convex, constraint in which I can separate what I don't know, what I don't know, this solution here, in which we can see that theta is a function of the exploration matrix up to -1. This is just possible if I can separate what I know with what I don't know. Do you remember in Gymnasium, very often we put on the left part what I know, on the right what I don't know, and then I divide. 2x equal 1. What is x? 1 divided 2. Just to give you the feeling. This -1 reflects that I can really separate what I don't know with what I know. Just a feeling, because to analyze the math is a little bit boring. We don't need in this course. Engineers, we can consider eventually together. I try to explain a little bit this picture, which is not necessary for us, but it's interesting nevertheless, because I have a measurement which belong to R up to n. The dimension of the vector y is m, because I have m component. I tell you this is not important for the project, but it's important to build or to give you the feeling of the abstraction. We have a vector, which is the measurement, which the vector is, how possible to say? Yeah, is inside the dimension m, is in the room, the space dimension m. And we have an approximating, let me say, structure y hat, which is inside the dimension Rn plus 1. What I am doing with this procedure can be seen as a projection. Projection and approximation. I approximate basically this red vector with the green one, but the green one is defined in a subspace is clear what I intend, in a room with dimension n plus 1, which is less than m. N plus 1 is the dimension of the number of coefficients. In the polynomial of order n, we have n plus 1 coefficients. This is a little bit an abstract form to see what we are doing. I try to approximate the red vector with the green one, as I can. Of course, depends on the dimension of the subspace in which green is defined, and of course depends also on the dimension of m. Typically, do you remember I told you last time, m must be much larger than n plus 1. Because if m equals n plus 1, we don't have an approximation. I get all points. Do we want to test that? No, we don't want, and then I insist again on this topic here. Because it's not an approximation. It's exactly to meet all points, which typically we don't do for different reasons, which I will repeat now. Last time I told you a little bit this. I will tell you here. Let me see, because I would like to open MATLAB a little bit. This I will tell you now. Let me try to conclude in 20 minutes, probably less, and then we open MATLAB the last 50 minutes to relax the lecture, to show you how easy is to do that. And next week we will insist about this MATLAB and so on. Do you remember last time I told you about these three cost functions? SSE is exactly what I told you until now. Huh? SSE is the sum of the error square. We can see from here. Exactly until now. Measurements minus its approximations, square, and I sum everything. Isn't it called the deterministic indicator? Because we don't have here any statistic elements. SSR is a statistical error because we can see that instead of each point, we have the mean value of the measurements here. I didn't put of the measurement. I'm telling you now because it could be improved the slide. Of course, this parameter here, or this parameter, this cost function is more statistical than the other one. That's because we have it. This here, do you remember, I told you is basically is the variance of the measurements. If I multiply by m, if I divide it, excuse me, by m minus 1 is exactly the variance. I don't know if you remember statistics. Basically, the SST is the variance multiply m minus 1. So actually is the variance. In fact, we have everything which I know. yi is the measurements, and y hat it's their its mean value, no? The mean value of the measurements. Yeah, here we have a possible graphical interpretation, but very important. Last time I told you, let me go ahead a little bit faster. And this slide here, which allows me to answer my rhetorical question, what is the best left approximation, which is not exactly an approximation, but let me say an approximation, or the right one. Yeah, to answer this question, even though the answer is a little bit strange, because you remember last time I told you that this equation, based on the definition which I have here, is an equation which is valid for an infinite number of measurements. We don't have infinite number of measurements. In this case, we have just two measurements. This means it's really an extremely approximating consideration. But in general, if I have a lot of measurement, what is the meaning of a lot of measurements? The meaning is exactly what is written here. That m much larger than n plus 1 exactly, or the n in general, of is much larger than n plus 1 is also much larger than n. This is for us something more clear what is infinite for us. Infinite for us doesn't mean anything. It's just a way to say large enough. If I say larger than n, something more, but also unclear. If larger than n plus 2 is enough, is unclear. But in any case, we understand a little bit better what I meant. Assuming that this is valid, this means I have m measurement much larger than n plus 1, or in general, larger than n. This means, in any case, this model here is more valid than this one. Because here m equals n plus 1, here at least m is larger than n plus 1. Because here n plus 1 is 1 and m is 2. Is much larger? Probably no, but at least large. Now, this equation here can be written this form. If I divided everything by SST, we have 1 here. We have here SSR divided SST, which I call R square. And here we have SSE divided SST. I can write in this form. This is clear, no? Again, 1 minus SSR divided SST, which I call R square, plus SSE divided SST. And I can put on the other side this SSE divided SST, and I have R square equal 1 minus SSE divided SST. Now, if I look this, and if I don't demonstrate, but it's easy to see that this R squared is a value we consider between 0 and 1, no? Can be demonstrated in an easy way. More difficult to demonstrate as R squared, for instance, is a monotonic function with respect to n, but at this moment, I don't want to, anyway, I need time to demonstrate. It's not necessary that I will do it. But look at this. Here, what we have here, why R squared is equal 1? R squared is equal 1 because SSE is 0. What is SSE? It can be 0 from here out also. No? It's 0 because I meet all points. If y hat meet all, excuse me, y hat I, for each I meet yi, this is 0. It's exactly what happens here. This means R squared equal 1. Why here R squared is equal 0? Is equal 0 because SSE is equal SST. Or if you don't like in this form, what is R squared? Is SSR divided SST. Do you remember? I can show you that SSR is 0. Also from here, because all points lie on the mean value approximation. Now we can see, excuse me, SSR is here, no? All approximate, let me close here. All approximating y hat I are on the mean value. Is not clear? Yeah, I try again. Look at this picture. Y hat I, these points here, equal y overline. Is written here. I didn't do any calculation, but assuming that I did correctly. If you consider here, for instance, 2, this value is 2 and this value is 3. The mean value is 2,5, no? Right? All this value is 2,5. But the definition of R squared is SSR divided SST. But what is SSR? But if all y hat I are on the y overline, it's 0. Basically, again, y hat I equals y overline, which means 0. Meaning, this approximation here states that we have the maximal error, statistical error, let me say, but the minimal deterministic one. You remember, SSE was defined as the deterministic error. Is always positive. Yeah, question. Before, yeah. You. Yeah. The deterministic error is defined by SSE. Because here, in order to remember, we don't have any statistic characteristics. Y is the measurement, y hat is the approximating function. SSR, which is here, we have a mean value, which is the basic, the most known statistic element. No, also in high school, I recall again in high school for everybody, we are able to calculate the mean value from the series of this is a little bit the definition. Makes sense if you look at what is written somehow. This means somehow this is R is oriented to the statistic error because we compare let me say the regressor with the most important element of the statistic. It's the basic knowledge. I don't know if I answered. Here, we compare what let me say, deterministically I measure, and the regressor, which is also deterministic. Of course. Theoretically, philosophically, here we have also something deterministic, which is given by the regressor, because I fixed it. But this is the way to just to say, of course, in the total separation between deterministic and stochastic error is not also here. We can see this from this equation. Here, SST is defined as the variance of my measurements. No? You remember here. SST is the variance multiplied by -1. The variance is something, I would like to say, stochastic, no? Something statistics. It is a parameter which we associate to Gaussian, any distribution, but it's variance in the sense. Equals this equation here, but of course, here we are in a mix, no? in this both between statistic and deterministic in the sense. But we assume that somehow we can split in this form. I don't know if it's clear. It's a little bit. First of all, it's an approximation. Again, we need an infinite number of measurements. We don't have, and but in any case, the nature of SSE is more deterministic. The nature of SSR is more statistic in this sense. Let me see if I can improve also my answer. I don't know if I answered, but yeah.
In statistical approach, is the mean value of the value the same or similar? Like, what's the difference between the value and
Like the why pattern.
Yeah, this is an interesting question. It's more difficult at this moment to answer. But if you consider that to answer this, we have to go more in depth in the probabilistic statistics. I don't know if you know the difference between mean value and expected value. You know. It's not the same. It's not the same. It's exactly your question. Because the expected value is something which just the name, but we expect it in a prediction form. And the mean value is something which you calculate from the data which you have. Here we don't speak about the expected value. We speak about mean value, basically with the data which I have. If I have time, I try to introduce some concept of the probabilistic, because the prediction is related to the probabilistic aspect. This aspect here, I will consider next semester, and you can also attend my class in Kalman filters. The Kalman filter, I try also to minimize this difficult concept in statistics, but I will tell you something more. We can understand better the difference between mean value and expected value. I don't know if you heard about that. Expected value, did you hear? Mean value, yeah, not from gymnasium. 1, 2, 3, the mean value I can calculate. What is the expected value? This is related with we have to define the frequency. Something more complex. What is an expected value? But it's not the same. Otherwise, we don't have two different words. I mean, it's not synonymous. And your question is, to answer your question, we have to go more in depth in probabilistic statistics, because the prediction is clear related to a probability, not to obtain something.
So like in this diagram, there's the line.
This line is the mean value.
No,
Mhm.
is it like
Yeah, no, again, it's a very good question. In fact, you remember here, between the information, could be considered. Yeah, could be considered. Also, let me come back on this. Again, excuse me, because it's everything's written, but of course, I have to select. Yeah, look at this. Prediction error. Basically, this here, as you told you exactly now, is the expected. Yeah, is more in the expected direction. Therefore, we can justify this sentence. Of course, it's a little bit too compact this slide to answer all questions. But keep in mind these questions. We can go in depth in the projects. And next semester, if you like this kind of knowledge, I offer in a very interesting course on related to the Kalman filters. You know this name, Kalman filters. This is a connection really between deterministic and probabilistic statistic aspect. I also there, because we are in bachelor, to minimize this mathematical aspect because it's extremely heavy, extremely. Yeah, but you're right. The line is the predict, can be seen in a prediction. Please pay attention. I use this word, can be seen. It's not the truth. It can be seen. As I told you, this is more statistic, more than it can be seen. What is, I don't know. Nobody can say. It's just the model. It's not true. Do you remember the beginning last week? It's just valid. It helps. Otherwise, it's not. Let me go ahead because I would like to show you MATLAB now. R square is, I told you, SSR divided SST, which can be seen in this form here. But this R squared is not a monotonic function with respect to n. You remember at the beginning I told you, I give you n. We will see in the next lecture how I can calculate, or how I can include also n inside the optimization problem. Because n gives the order of the polynomial, but in general can help or can determine the family. Could be trigonometric, could be exponential, because n in the polynomial is connected with the number of coefficients. Number of coefficients is n plus 1. But we will see that the number of coefficients, that's what we do really practically, is also connected in the Fourier analysis, in the trigonometric function. Also, let me say, with the number of frequencies which I consider in a possible approximation, I will consider the Fourier basis of Fourier function. This means n is extremely important. But what is the problem? Two problems we have that I don't have time to show you, but believe me, R square is in a parameter included between 0 and 1. We can discuss later how this is easy to do. And then is the monotonic function with respect to n, meaning increasing n, we can see also here, we will increase R squared. This means R squared is not a good parameter to determine n because it's not convex. Remember, I told you about this convexity before when I calculated theta. The problem of the convexity of the cost function remains. If you don't have any convex function, no chance to calculate the optimal point. Now I speak about optimal point, not only of the minimum, but remain of the minimum. We will see that we can also consider in another context maximum and so on. Remaining with the minimum because it's a least square, no? Remain on the way. We modify, and we will see next week, this R square adjusted in an heuristic form, and then we don't have R square adjusted, but we don't have R square, but we have R square adjusted, in which we try to modify our R square considering a function of the number of points We can see a measurement in the sense. And the parameter P, which basically is the number of the coefficients. We can see that in this sense, we can have the possible convex elements or cost function R square adjusted. Why that? Because we can see if, please pay attention now, SSE is a monotonic function because increasing n, I will decrease SSE. Example to keep in mind is n equals 0, n equals 1. R square will increase. And this will remain also if I have m points. I don't have time to show you, but believe me, and we can see from this example. No? Of course, here the change is abruptly from 0 to 1 because we have just 2 points. This means this is increasing. If n will, I will increase. But what happens here? The denominator will decrease because if I increase n, I will go toward m. This means m means something which is close and closer to m. This means we have something which can be, in any case, considered, can let me say, end up in a convex function, because as I told you here, we have something towards 0, SSE divided something towards 0. This means it could be that we can find something which is not necessarily convex. And we will see that it works. But it's just a possible modification. We have also other modification of R square. Probably you know other different cost function to be optimized. At the end, we will see now next week. Let me go to MATLAB because I would like to show how easy it is to implement. We will see that this kind of problem can be defined in a possible minimax problem of R square adjusted, in which we try, and then we will see with MATLAB, we try to maximize the function R square adjusted with respect to theta, and then contemporarily to minimize with respect to n. We will see in detail next week. Here we are ready basically because I will consider next week this very quickly, and then we will see with MATLAB some exercises in which I will optimize n and theta in this minimax problem, which can be seen in min. I don't know if it is visible because the maximal with respect to theta of R square adjusted is the minimum of respect to SSE respect to theta, because when this is the minimum, we tend to 1, which is the maximal R square adjusted. But in the meantime, we have to find the minimum of this R square adjusted with respect to n. We have two variables, n and theta. Now, I conclude with this. If n is a variable, we end up in a non-convex problem, and this could be a nice project to be attacked with the particle swarm optimization methods. Probably you know particle swarm optimization method. It's not here yet, but I will tell you. Why is not convex the problem? Because as I told you, if n is unknown, the constraint cannot be split in what I know and what I don't know, because here in this element here, we have what I know, which is x1, x2, xn, but mixed with n, which must be calculated to be optimized. But we will see heuristically next week how I can proceed. And then in some weeks, we will see how a possible method to calculate with software directly without try and error. Is not solvable with this method if n is not given, because basically, do you remember this? I cannot invert, because here it's what I know, and here is what I don't know. Excuse me, here is what I don't know, theta, which will be calculated with respect to what I know. But x is mixed with what I know and what I don't know. I cannot split the problem. 10 minutes, give me 10 minutes. I will exceed just 5 minutes to show you MATLAB. MATLAB is known, no, it's known a bit, I introduce quickly and I show you the software, even though I will come back next week. No, soon. Okay, MATLAB is a software, and a really powerful software, which helps. Let me open MATLAB. In, let me say, in scientific calculations, and in particular, if we have to do with matrix, but not only. MATLAB means, let me open this one. I have also difference release. This is a little bit old, but quickly I found this. Not only calculation with matrices, but in particular, no, and therefore, I told you the name. To attend these lectures, I think I would like to say is also enough to come here to learn a little bit MATLAB, even though I am not able to hold a course on MATLAB, because we need a course just for MATLAB. Here is much more. This means I will tell you some procedure. I will upload some working files. Otherwise, we don't have time because MATLAB is a really huge program with a lot of thousands macros, commands, structure in graphical element like Simulink. Is extremely complex, really. We have to go to MATLAB slowly. This is probably one of the first approaches for you. But of course, I cannot really explain. But we will see through our examples that at the end you will be able to at least to use in our context. Just a second, I show you. If you click twice on the icon, you can open the file, I hope. Yeah. Let me share. The program appear in this form. Let me share, which we can see, some, let me say, regions, let me say so. Here I have to answer no, because here I have in a toolbox, my toolbox on wavelets. We can see that you have 4 places, let me say. We can see here in the middle, this moment is blocked. Let me see. There now. Here in this form here is basically the command window. This can be used. It's blocked. Oh, I share. Yeah. It's blocked. It doesn't work. A second again. Now. Yeah, here, for instance, if I write 1 + 1, we can see answer equal to. We don't need MATLAB to do that, but just to show you that here on the right part in the workspace, we have a variable or a parameter answer, called A and S with the value 2. Here is in a region in which we will see we can put comments. 1 + 1 is not a command. Clear is not a command. If I put again clear, I will clear the kernel of the MATLAB. We can see that the variable A and S is not present anymore. In the middle, we have the most important part. We will go in depth on this using when I will clarify particle swarm optimization method, in which we can really realize complex programs, extremely complex. For instance, look here. Here, excuse me. Here is what I will tell you in the next weeks about we will do exactly this together. The particle swarm optimization method, which is a solver to attack not convex optimization problems. Yeah, we can really write complex programs, really complex with if, while, for files, for loops. You know this a little bit, engineer, of course. For loop, if loop, while loop, iteration, engine. But we will see a little bit. But again, the goal here is not directly to learn MATLAB, is not directly to learn programming. This should be done by self. No? Yourself should be, but based on my program. No? That is, it should work. Now, to our problem of today. I don't tell you now what is this one, but this is intuitive because we are working on Windows. We can see here the path. We can see here the path. We'll tell you a little bit next week, but this is trivial. This is the path of Windows. If you work on Linux or the Unix, it's a little bit different. In our lab, we have also. This is in the Windows system. It's MATLAB, which is working under Windows. Let me open the file in 5 minutes to show you. And then we will conclude. I will upload, but this can be uploaded also next week because it's really done very quickly. Okay, you have just one lecture. Let me see in the... If I find, by that. It doesn't find. Yeah, okay, I found it. Yeah, look at this. I will upload, but next week we will come back here. Look at this. Forget at this moment this global DT theta. We will see in the next. Look, we have a vector, which is the vector of phi. You remember this flux? Y. This is Y. Please pay attention. MATLAB is intuitive. Is a vector. In this sense, is a row vector. If I consider this apostrophe, is a column vector. Apostrophe is interpreted in MATLAB as a transposition. You know transposition? You don't know. Transposition means what we have in this form, if I put apostrophe, will be in vertical. I transpose the matrix means I change the row with column. Roughly explain. Here we have a vector, row vector. It's intuitive because we have, as you write, 5, 4, commas, and then if you put apostrophe, it means it's in a column. Here I multiply everything by 10 minus 3 because it's the flux at this value. But if you have a different value, you can work also with row. I told you, I show you this because I would like to show you something MATLAB. Look here, for instance, the exploration variable x, which I called here I, because the current typical is I, is not organized in column, but in a row. Why that? Because didactically I try to explain a little bit MATLAB now. 3 minutes. This semicolon is just formally there. If I don't put the semicolon, like here, this means this line A, x5, will be printed on my command window. If I don't want to print, I have to put semicolon. It's not an strong active function, just to show you the results. Look here, very important for you, your question. The line 8. The line 8 I called x5 because I am considering here, without optimizing the index n, the polynomial order 5. Why that? Because I consider this. Some reasons are there, because if you look at the measurements, here we will see that we have a symmetric measurement with respect to 0. Do you remember these odd functions? Ungerade Funktion. F of x, f of minus x equal minus f of x. Therefore, intuitively, clearly, this is a little bit, is not exactly the measurements. It's a didactic example, because you can see here 5 minus 5, 4, 9 minus 4, 9 really is not exactly symmetric. The reality is not exactly symmetric. The symmetry is just an abstraction, but didactically, I would like to show you. But the hysteresis is something odd function, but it's not exactly odd function. In math, we say odd function, even function, no odd, not even. I don't know if you remember. Could be neither nor. Typically, in the reality, is neither nor, but this will give us this result, the optimization methods. Here is not optimization, just the representation. Look, this element here, I am concluding, this element here is exactly the exploration matrix. Now, your question, you can see here, we have I apostrophe is the column of the current. Let me show you what I intend. What is the presentation now? I closed the presentation. Did you see I apostrophe dot? This means each element. Again, to your question. Let me share. Look here. I don't know if I share, no? X1, X2, Xm colon is our I1, I2, Im, the vector I, each element dot in MATLAB up to 5. I will consider this column of the current vector up to 5. Each element, this means each is dot in MATLAB, in the language of MATLAB. And I do the same for the rest, but of course here is the vector, the exploration vector up to 4. And going right, up to 3, up to 2, up to 1, and then up to 0. Therefore, we have ones. Let me come back here. I am concluding because now we have the solution. What I'm doing now? I don't know if I MATLAB. Where is MATLAB now? Here. Look, as I told you, the column. Why the column? Because of this apostrophe. Here we don't have apostrophe. If I put apostrophe here, I have to cancel this apostrophe. Column of the measurements, each element up to 4. Because you remember in math, we are not able to define the vector of square and the vector of 5. But we can define each element, each component. Ready. Here we have ones. We can see here in a column of 15 ones. Why that? Because in our case, we didn't consider 8 measurements as in the lecture, but 15 just. Why? Because we have 15. This is the number of errors. This is the solution. What I told you the solution, do you remember? X, exploration matrix, transpose, multiply X, invert, multiply X transpose exploration, multiply phi. I didn't demonstrate mathematically, but I told you in the equation. The rest is technical aspect, which I will tell you next week. This is the solution is already here. Theta compress my function. I come to you with your question, but we will restart next week from this. And here we have the theta, we can see here, the value of theta. We will see why some of them are 0. I will clarify. It is related with this odd function. And here we can see, ideally, the solution. We will go in depth next week together with MATLAB. And the idea of next week to go in depth on this, again, a little bit to repeat, because at the end is a little bit too fast. And then we will see always with MATLAB how we can optimize using trial and error, also considering n when the problem is not convex. When the problem is not convex, we don't have an analytical solution directly as today. But again, this is just the graphical representation. We will see again R square, square adjusted, and so on in MATLAB, but the solution is already in MATLAB workspace. That is the solution to everybody at home. This is just its graphical representation, which itself doesn't mean anything, because we should be calculating R square adjusted to be to judge what we obtained, but the solution today. 1 second, if I am able to share, and then I come to your question. The solution today is already here. This data, which is compressed, my blue line. This parameter, this 6 parameter, A0, A1, A2, until A5, 4, because I have 5 parameter, 6. Yeah, polynomial order 5, I remember well. No? This means 6 parameter, n plus 1. Is there. This is the solution. With this solution, we can reconstruct graphically also the curves. Why we need the curves? We need the curve because, as I told you, practically, really practically, we want to describe the phenomenon which is continuous between, in our case, -5 and 5, even though I have the partial representation. We have just 15 bars. This is a little bit we will go more in depth on these issues next week. Questions?
I just wonder how the projects will look on. So, I mean, roughly gets this part, but how could the project look like on this things?
Looks like in which we can apply intended.
What?
It looks like what you intended with the words.
What the projects
The
about.
project. Yeah, it's too early to speak about the project, but if you think that these characteristics could be a characteristic of a motor, in which we can use in this, I will show you this for the engineers. Using this hysteresis curve, you can calculate the inductance of a motor. I show you this, we can do that. And then if I give you, for instance, in the project, in the sense, I give you the structure of a motor and I say, this is the measurements, build the model, the optimal model. And the optimal model is the model which try to approximate in the optimal way, for instance, the inductance. The inductance that is, if you have the coil and so on. This could be a possible application on this, because you need L, inductance, and the inductance practically came from some measurements. This could be an approach. In fact, at the beginning, I will show you this global d theta. We will see is exactly related to a project in which I determine didactically, but I can do really in real problems, the inductance related to these measurements, phi, flux, related versus current. This I do. This I will do it. So we'll be more concrete why this could be important and useful also in a real project. Think about L, no? The inductance.
So, for example, we just measure the outputs of electric generator or something like this, and then we calculate the curve, and then we try to say what mean power output is.
Exactly. In any case, can be used in extremely different context. I will show you a really suitable context connected with this example. I will reuse this example. You can believe me. This is related to another project, this global DT theta, which is here at the end. And you can really concretely see how we can apply such kind of non-parametric modeling, I would like to say. for dynamical systems. We consider an RL circuit here in the lecture. I cannot really offer really complete projects because it's really heavy for the volume of information. Then this probably is important just for engineers. But in any case, for everybody, it's important to see how we can apply such kind of methods. Thank you for the question. I will have an example. Exactly inductance of an RL circuit. This is possible in such kind of lecture. Other questions, even though I have a meeting in 2 minutes, but I have time for a couple of questions. Otherwise, next week, you know? Thank you. Thank you.